Welcome to 24th lecture of video course on tribology. Today's topic is viscosity variation. We want to incorporate viscosity variation in Reynolds equation, or at least get a feel of need of that variation, how that variation is going to change the pressure distribution. To continue with this topic, I prefer to refer previous lecture slides, couple of the slides. We say that we derived Reynolds equation and then we found hybrid solution, and to establish hybrid solution we discuss about the finite difference method. Compare finite difference method results with the hybrid approach and approach 1 and approach 2, and figure out that hybrid approach provides a very good results without any computational time compared to finite difference method. Of course, in addition to that we refer it is computational time in these days is not very costly. That is why we do not have to worry about the computational efforts, but at least the time, but efforts are important, how to develop computer program and how to proceed the iterations. Those things were discussed, and in previous lecture one slide was given on viscosity variation with respect to pressure. So, I am just going to repeat that slide. So, in this case so the Reynolds equation with the pressure viscosity relation. In other words, viscosity is a strong function of temperature as well as the pressure, and this slide shows viscosity variation with the pressure. Generally we use exponential law. We say that viscosity is viscosity at ambient pressure into exponential of alpha p, depends on the pressure. As the pressure increases, viscosity is going to increase. That is a simple case. Also we say that if any liquid is subjected to compression, viscosity will increase, and using this relation, this table was shown. We say that when the pressure is 10⁵ Newton per meter square or 10⁵ Pascal, viscosity multiplied with the ambient pressure, particularly this. So, viscosity will be 1 unit. I am not just multiplying with a Sandy stroke or Sandy poise or anything. Is just say that viscosity is 1 unit. For time being we are using only multiplication factor. Then if the pressure increased by 10 times from 10⁵ Pascal to 10⁶ Pascal, or we say 1 megapascal, in that case we are able to find 1% increase in viscosity, or multiplication factor is turning out to be 1.01. So, 1% increase in viscosity. Further increase in the pressure by 10 times, you say 10 megapascal, we are able to find 10% increase in viscosity. If I follow this pressure viscosity relation, many times we call as a Barrows relation, and it has been given by the authors and they have used extensively. As pressure further increases, viscosity is going to increase. We say that at 1 gigapascal pressure, viscosity variation or viscosity increase will be at 22 times. That is a significant increase in viscosity, which is a substantial viscosity variation, and that need to be incorporated in Reynolds equation. This is a simple Reynolds equation, steady state. We are assuming only tangential velocity in x direction, and film thickness variation is also along the x direction. There is no film thickness variation in z direction. In addition, we are assuming that plates are fixed, they are not moving relative to each other in y direction. That means there is no squeeze film term. If we substitute this relation in a Reynolds equation, what we get is something like this. Instead of eta, we are writing now eta 0 e power alpha p. That is a 1. Rearrange, we say the eta 0 will be constant. It is atmospheric viscosity is constant in this case. It can be taken out and we can shift to the right hand side. So, this instead of 6 u, now we can write the 6 eta 0 u, and this alpha power. So, e power alpha p can be rearranged and a numerator, and you say that in this case it will be e power minus alpha p in x term as well as in z term, and we need to rearrange the pressure in such a manner that linearity comes back. While in this case we know very well alpha p is here and p is here also. So, this is a highly nonlinear term. It will be difficult to solve this term. So, that is why we require some sort of mathematical manipulation and rearrangement, substitution. You say let us assume one quantity q and name as a reduced pressure, and expression of reduced pressure is 1 minus e power minus alpha p divided by alpha. Now, what is the advantage of this term? You see, when we differentiate q with respect to x, 1 will be differentiated to 0, negative will remain there, and this when differentiate e power minus alpha p, negative will be cancelled out, obviously they turn out to be positive, and this will retain e raised to minus alpha p and this pressure term, pressure gradient term. We required this term only. Here we are able to see e raised to minus alpha p into dp by dx, and we are able to get equivalent term for that, that is a d variation of q with respect to x. We can substitute it here and we can rearrange. Now, this is the same equation as equation number 1. In a way we started with that equation. Mathematically there will not be any change to solve this pressure equation or this pressure equation. Efforts will remain same except the boundary conditions, because in this case pressure is a 0 at the boundary condition. We again substitute pressure 0 here, it will turn out to be 1 and q will also be 0. So, pressure variation can be simply replaced with a reduced pressure variation, and boundary condition also can be maintained the same boundary condition, and we can solve this equation with any of method which we have discussed, approach 1, approach 2, hybrid approach or finite difference method approach. It is time to think whether when we are doing this kind of a conversion from P to Q, or we are trying to incorporate viscosity variation, will there be any change in results. As this table shows that as the pressure increases from atmospheric to the 10 atmospheric to the 100 atmospheric, viscosity variation initially increase in a not substantial, maybe initially is a 1%, then 10%, then 171%. So, we need to see these results. For that purpose, we have a couple of examples, and of course, in this case before moving to the next slide, I want to emphasize that no consideration of the change in the shape of the surface and the high pressure is assumed or is considered. We are not considered change in the film thickness, we are not considered change in surface of the solids which are coming into contact. Otherwise, under pressure we know very well it will deflect or surface will be deformed and film thickness variation will be there, but we are not accounted for time being. We want to go ahead with the one by one. Initially we are using only the viscosity variation. Now, this is pressure relation. What we said in this case, earlier I showed a non-dimensional pressure, while here we are showing dimensional pressure. So, we know what is the magnitude of pressure, what is the value or maximum value of the pressure in this case. This is maybe x direction, z direction, we have same number of nodes, so it does not matter much to us, but this is a vertical, like so that is a z axis in this case is obviously in this case particularly we can choose a y axis because we have selected x axis and z axis and along the axis and perpendicular to the axis, and this is the pressure axis. Maximum value comes some roughly here is around 7 into 10 is to 5, obviously 7 bar or 7 atmospheric pressure. This clearly indicates that viscosity is not going to vary significantly, because earlier in the previous slide we showed that if it increased by 10 times, if viscosity pressure increases by 10 times, viscosity variation will be 1%, and that is what we are trying to understand from here. Now, when we are accounting only the pressure variation, we are not counting the reduced pressure, we are not substituting the relation eta is equal to eta 0 e to power alpha p. In that situation what we are gaining? We are gaining almost same value of pressure, maybe there hardly any percent change in the pressure. Here we are using Q, or this chart is P, but we have used Q in Reynolds equation, got the results for Q, and then finally we have converted in P. So, this is again a P relation or P axis, this is a P axis, you can see the magnitude almost the same magnitude in both the cases. We say that in this case we are accounting the pressure viscosity relation. In this we have not accounted pressure viscosity relation, but magnitude change is not happening, or we say that what is the pressure in this case, same pressure is happening in this case also, not significant variation. So, when we do not get a change in the results, then there is no point to account this kind of relation. I say that low load bearing cases we should not account the reduced pressure or viscosity, pressure viscosity coefficients. We can simply use this as a Newtonian fluid having constant viscosity. However, there is a point to see if viscosity increases, or if we are thickening the oil, we are going with a thicker oil. When we go for the thicker oil, we are able to see there is a pressure is increasing in a magnitude. In earlier case, the previous slide, it was 7 into 10 to 5. Now, in this case, we have increased viscosity by 20 times. It is earlier was a 10 millipascal second, here we are considering a 200 millipascal second, and the viscosity of the lubricant has been increased by 20 times. Base oil viscosity itself is increased by 20 times. Then in this situation what we are able to get? We are able to get a roughly 1.25 into 10 to 7. So, there is a point or we say that in this case particularly 12.5 megapascal pressure comes, viscosity will vary to some extent, maybe say 1% or slightly above than 1%, and we should be able to get effect on pressure variation also. So, this chart is without accounting the variation in viscosity, and this chart is to show or account the variation in viscosity, or in this case first Q has been obtained from the Reynolds equation, and subsequent to that the pressure has been calculated using this relation, and this vertical axis is representing the pressure variation. We are able to see the difference. You can see in this case the gap between the peak, this red peak and this line is countable, while in this case this gap is reduced. That means pressure is increasing, or another word, when we are counting the pressure viscosity relation, maximum value of the pressure is changing, it is increasing. So, there is a point to account the pressure viscosity relation when maximum pressure is going to be more than 10 megapascal. In this case particularly it is 1.25 into 10 to 7 pascal, or 1.25 into 10, that means 12.5, and 10 to 6, that is a megapascal. 12.5 megapascal is the max pressure, and we are able to see there is some variation. So, from 12.5 it is maybe going for the 13.5 or 13.75 megapascal. There is there is a change in pressure in this case. Now, there is another thing to see is that this is only the viscosity variation. We increase the viscosity by the 20 times, or we say that initially in previous example viscosity of oil was a 10 millipascal second, while in this present example or in present case we have considered this as a 200 megapascal 200 millipascal second. So, 20 times increase in viscosity. Now, we can see that this variation with increasing velocity also. We know very well hydrodynamic action basically depends on the relative velocity. If velocity is continuously increasing, then pressure will vary, load carrying capacity of that tribopier will increase. So, in this case we are trying to see the effect of relative velocity. If I am increasing relative velocity, what is going to happen? You can see with the increase in the relative velocity, initially it was a 1.25. Of course, we are maintaining the same viscosity which we have shown in previous slide, that means of 200 millipascal second. Now, when velocity is increased, initially this before the increase in velocity, the maximum pressure was roughly 12.5 megapascal without accounting pressure viscosity relation, while in this case it is turning out to be 35 to 37 megapascal. That is 2 times. That means the velocity has been increased by the 2 times or 2.5 times. Now, if we account pressure viscosity relation, we say that we in Reynolds equation we use a Q, and once a Q has been determined, we change to the pressure, we convert to the pressure, and that pressure is been plotted over here with the x and y x and z axis. We are able to see the maximum pressure is crossing the 4 or is crossing the 40 megapascal, while in this case it is not crossing the 40 megapascal. The substantial change. This is what we try to convey when we incorporate viscosity variation in Reynolds equation. There is going to be change in a pressure, and if we do not account, we are going to predict the low load carrying capacity compared to what it should be. This is the reason why most of our human body joints are made with elastoatomic lubrication, where the pressure viscosity coefficient is also comes into picture, and we need to see the thickening effect or viscosity thickening effect in those situations. We are able to see here the clear difference is more than 4, maybe say 4.2 or 4.3, while here it is lesser than that, maybe 3.5, 3.7, and substantial change in the pressure in this case. Here we are saying that viscosity we have maintained 200 millipascal second. Initially velocity was 20 meter per second. Now, velocity has been increased by 2.5 times, so it is turning out to be 50 meter per second. Of course, in these situations we are not accounted change in a geometry due to pressure. We know very well under high pressure every body is subjected to deformation. If we account the deformation, film thickness will vary, film thickness will increase. If film thickness increases, then load carrying capacity will come down or pressure will come down. So, to some extent they are self adjusting. First one cause is a pressure increase, deformation will subsequently to that, or deformation will occur because of that, and that because of the deformation film thickness will increase, because of increase in a film thickness pressure will decrease. So, there will be self adjustment, or what we are predicting just because of the viscosity, there is a possibility when we account a deformation pressure again will come down to some level. Now, this was related to pressure viscosity relation. We know very well, or we have studied in when we were discussing about the liquid lubricants. The liquid lubricants are a strong function of temperature. With increase in the temperature, viscosity of liquid lubricant decreases, and we gave a 2 relation. We discussed 2 relations there, which is Vogel's relation and the Wallis relation. What was the Vogel's relation? It was a viscosity or dynamic viscosity is equal to some viscosity at the ambient temperature, again exponential. This is the one constant and theta another constant, and in this case T is the temperature in centigrades. And but we can say how K is interpreted, that it is the inherent viscosity, maybe a 20 degree centigrade, 40 degree centigrade, what will be the reference temperature which we are accounting initially, that will. Now, if I account if I want to substitute this viscosity relation in this Reynolds equation, then what will be the problem? If I substitute directly, I will find when there is a temperature, viscosity is not represented in terms of pressure in here, but it is represented in terms of temperature, and in Reynolds equation we do not have any temperature term. This is the reason why we require a energy equation, an energy equation to be accounted, to be incorporated, where the pressure and temperature relation may come one way or another way. There is some sort of coupling between pressure and temperature that can be accounted, and then based on the simultaneous solution of pressure and temperature, we can find out what will be the variation in viscosity with respect to temperature. That is a slightly difficult slide, but we can drive those equation. But before coming to this, we will try to take very simple case which is more popular, and people at the initial or the first phase they start with that kind of relation. This is what I showed this slide during the discussion with the lubricant or discussion on the lubricant. We say there are different SI grade oils, there are multi-grade oils and there are some monograde oils. These two are monograde oil, these two are monograde oils, and this is multi-grade oil. And what we express that viscosity will vary at the 40 degree centigrade. Suppose this is a 32.6 centistroke viscosity, at 100 degree centigrade we are able to see that there is significant decrease, and at 130 degree centigrade further decrease in viscosity, and that need to be accounted. And most popular method as I mentioned from measurement point of view, because mostly the viscosity is measured in a centistroke, and that is a kinematic viscosity, is not a dynamic viscosity we are using in Reynolds equation, and this has a log plot. You say there is a using Euler's equation. First good thing is that we have only two constant, while using Vogel's relation we have three constant k, b and theta, they are three constant, while Euler's equation has a two constants only, constant this constant and c as a constant. What is the difference? In Vogel's relation we have to substitute temperature in terms of centigrades, while in Euler's equation we generally substitute in terms of Kelvin, that is a 273 plus centigrade will be temperature in centigrade will be expressed over here. So, when we incorporate these relations, we can see the variation in a temperature, obviously variation in viscosity with the temperature, but we need to incorporate the temperature one way or another way, either in a Reynolds equation or with some other accessory equations. As I say, that one of the equation is energy equation, where we can find out how much heat is generated, how much heat is convected and how much heat is conducted away. While simple or most common use, as I said in the beginning, people generally prefer, that is a Petrov equation. Petrov has used a very simple formula to say that how to calculate friction, because temperature is comes because of the heat generation, and heat generation comes because of the friction, and friction can be represented with the shear stress of liquid into the operating area wherever the this operation is happening. So, area into shear stress, and for Newtonian fluid we know shear stress can be represented as viscosity into the velocity gradient. Here the velocity is u or v, whichever is because Petrov most of the Petrov relation show that he represented velocity is a v, not u. So, but in this case we are use u by h viscosity. Of course, it can be interchanged easily. You can see here what the diagram indicates, the viscosity is velocity is a v, there is a gap film thickness, and there is a velocity v here, but with this here is velocity is 0, that means relative velocity is v. And this is what Petrov has developed this equation. It was generally for the one fluid film bearing. We can develop a similar kind of relation for all other bearings, or we can say that open up this complete circumference, the old circle is there, we can open it up and develop the surface something like this. So, we can calculate what will be the friction force at this interface. So, F friction force can be given in terms of viscosity, in terms of velocity per unit of film thickness into area. Now, for this kind of geometry we can say that the pi dn, velocity is a pi dn, or with the rotational speed of the shaft which will be accounted, and surface speed or of the shaft will be pi dn, or 2 pi into r is the radius of the shaft in this case, and area can be given as a pi dl, that is again the whole circumference into the length of the shaft which is within a bearing. So, area which is really shearing the liquid is given as 2 pi into r into L. Now, we substitute this relation, what we find here, the friction force is equal to viscosity, or we say that dynamic viscosity into 2 pi r n, this is the velocity, and into the surface area which is responsible for the shearing of the liquid, as a 2 pi r into L. L is the length of the bearing, or the where the shaft is shearing the liquid, particularly that area. And here the C is a clearance, C is a clearance between the two surfaces, geometric clearance, or we say the particularly radial clearance when we are referring this kind of tribopair. So, once we know the frictional force, we can simply find out heat generation. We know that the friction force into velocity, tangential velocity is going to give us a heat generated. What is the heat generated at that interface, that can be calculated easily. Now, once we know the heat generated, we need to find out how this heat has been conducted away. So, we are able to see that in this situation we are using additional equation. It is not a Reynolds equation in this case, we are not using a Reynolds equation at all in this case. We are using additional equation, simple algebraic equation. We know the friction force is shear stress into area, and shear stress for the liquid can be represented in terms of viscosity into the velocity gradient and to area, and then we have represented those values and finally figure out heat generated is friction force into velocity. As I mentioned that temperature rise can be determined to find by finding how much heat is conducted away or convected away. If fluid film bearing and there is a mass circulation and the continuous flow of the liquid, most of the heat will be convected away by the lubricant. There will not be much heat conducted away because there is a continuous mass flow rate. And if that is a situation, we can take very simple case. We say that whole of the heat is conducted away, convected away by the liquid lubricant, and we need to account the properties of liquid lubricant. We can assume the density of lubricant is 860 kilogram per meter cube. It is slightly lower than water density. This is the heat capacity, the 1760 joule per kilogram centigrade. This is one of the very common figure often quoted for all the liquid lubricant. If you do not have anything, we can go ahead with this kind of heat capacity. And another thing, we have to use it in Petrov equation. We are just taking assumption that radius, geometry, the shaft radius or the bearing radius is much larger than the clearance between the surfaces or clearance at the interface. That is also genuine because if this ratio is not very high, Reynolds equation cannot be used. So, to make sure that Reynolds equation is applicable, we can find out this, we can use this assumption, which is R by C is 1000. It can be lesser, it can be more also, it can be 900, it can be 1100, depends on the different configuration, but just for the first initial exposure or to get a feel of the temperature rise at the bearing interface or the tribopair interface, we can assume these data. Okay. So, in this case what we are saying that total heat generated was earlier in previous slide calculated, and whole heat is convected away by the oil film. So, heat generated in this case is related to viscosity, related to the velocity. Velocity is coming 2 times the velocity square, 2 pi r n here, 2 pi r n here, and this is the area or surface area and clearance. While heat convected is a mass flow rate, whatever we assume, into heat capacity into temperature difference. So, with this we can find out what will be the temperature difference. If we know the mass flow rate, if we know the Cp, and of course, the mass flow rate can be figured out, depends on the volume available into movement density. The density is here rho, and what is the volume available, which is the pi d n into clearance into length, that is a volume, and we assume that only half of the surface is convergent and half is divergent. So, we are taking 50% of that, and this is what we say the mass flow rate can be represented in terms of the geometric parameter. It is of course, basically derived by the velocity or rotational speed. If we are feeding at some pressure, then we should add that term. Here in this case, basic assumption is that there is no feeding pressure, there is no supply pressure to the liquid. Is happening because of the suction effect which is generated by the velocity, because of rotation, and rotation itself is pulling the liquid in a tribopair or in this interface. Okay. If I say that some liquid is open or the hole is open to the liquid, and due to rotation there will be some sort of vacuum creation, or there will be some suction creation, and that liquid is coming in the bearing because of that, coming in this geometry because of that. So, this is a mass flow rate, then heat dissipation, and then temperature difference can be given by this relation. Now, we know very well that most of the data are known to us. In this case, R by C, we are already assuming Cp is for liquid, generally constant value, can be used directly here, density terms, and 8 pi square is simple constant. So, we can substitute this value and we can say the temperature rise can be given in terms of viscosity and in terms of rotational speed. Of course, if there is no radial bearing, or we say the radial geometry is not there, then in that case we should use a tangential velocity term. If we substitute this value, what we get? Temperature difference is given as 52.2 times viscosity into rotational speed. Now, we can clearly understand from this relation, if viscosity is increasing, temperature rise is going to increase. That is very interesting thing. Increase in a viscosity is going to increase the temperature rise. Increase in a temperature rise is going to decrease viscosity. So, it will be a iterative loop to come up finally what will be the result. Higher the viscosity, higher will be temperature rise. Higher the temperature rise, lower will be viscosity. So, it is an iterative loop, it is a closed loop system. In addition, what we say here is the here the velocity or the rotational velocity. Say that if the n is higher, temperature rise will also be on higher side. That is a genuine, and we know very well in most of the tribopairs, if there is a high sliding velocity, then temperature rise also will be on higher side. Of course, in a previous slide there is another relation has been represented, so what we say the simplified Vogel's relation. Here we are saying that instead of K, we are writing N at the initial level or inlet temperature, and T in is inlet temperature, obviously the ambient temperature. Here the B is only the constant. If we know the 40° temperature or the environment temperature, we can directly use this viscosity. In addition to that, there will be one additional constant, that is a beta. We can figure out that the viscosity is known for some other temperature. Now, if to understand further, we can simplify, we say that let us assume capital N is a 900 rpm, and we substitute that, we will what we get from this. Of course, we have converted to RPS and then found this figure. We say the temperature rise is equal to 783 into viscosity, and this viscosity will be in a Pascal second. Even though we have represented viscosity here in a millipascal second, but this viscosity will be in Pascal seconds, and we can see the effect of this variation. So, when operating temperature is this or viscosity is this, and we try to find out what will be the temperature rise, we are able to judge the temperature rise something like this. So, when the viscosity is 32.6 millipascal second, you convert it, we are able to see the temperature rise at 25° centigrade for this viscosity. With the increase in the viscosity, temperature rise is increasing. You can see here that 140 millipascal second viscosity, the temperature rise goes to more than 109° centigrade. Naturally, there will be drastic reduction during operation. However, if we account actual temperature, or we say that if I account the temperature is 100° centigrade, and we are trying to figure out based on that what is effect of this viscosity, what we get is the temperature rise only this much. That means T in we are assuming 100° centigrade, and when we are counting this viscosity, we are able to find only temperature of 4.3 or 4.4° centigrade. To compare this 4.4° centigrade with the 25.5° centigrade, when we are counting this viscosity, keeping everything else, all the geometry parameters same, all rotational speed and everything same, with this viscosity temperature rise is this much, with this viscosity temperature rise is this much, all other parameter remains same, and that is also visible or can be judged from this relation. Similarly, when we go for the high viscosity, we say that in this 20.5 is viscosity 20.5 centistroke, then we are able to see the temperature, we are able to see that this is 16.5 temperature rise, while here is 117 and the temperature rise is 91.6. So, only one point to be kept in mind, these are the kinematic viscosity, and we need to account the density of the liquid when we use this temperature rise effect. That is important. And another point which we want to emphasize is that there is a significant change in temperature rise because just change in the viscosity. We should account this viscosity variation in a Reynolds equation. We need to really drive the energy equation to get the results. If we do not use the energy equation and assume there is isothermal analysis, there is no temperature change or there is no variation in temperature, we may not get a good results. That is why we say in hydrodynamic lubrication, increase in viscosity, increase the load capacity, but also increase the friction. We require solution of the Reynolds equation with energy equation. By solving Reynolds equation alone will not give the good results. We need to use some supporting equation. In this case, we showed this effect or effect of the temperature rise using Petrov equation, but in reality we need to account all the effects. We say we need to account the energy conducted away, convected away, and maybe if there is a possibility of radiation in some environment, we need to account those and then find out what will be the temperature rise, and based on the temperature rise we need to figure out what will be the viscosity, which is going to affect overall pressure generation. This was related to viscosity variation and viscosity variation with the temperature, viscosity variation with the pressure. But when we were discussing viscosity variation with the pressure, we say that we are not accounting the change in surface geometry, change in the film thickness, change in obviously the deflection of the surfaces. Without that, it is only the half treatment given to the elastrodynamic lubrication. To account both the cases, viscosity variation as well as deformation, we need to find out what will be the elastic deformation under different conditions. That is why this slide comes. You say that we need to find out what will be elastic deformation of the surfaces. Initially, we are taking very simple geometries, maybe say sphere on a sphere, cylinder on cylinder, and more or like they are convex geometries. We can after driving the equation, we can extend this to the concave geometry also, more like or flat geometries also. What is meaning of this elastic deformation? We say that in under compression load, surfaces will be subjected to elastic deformation over a region, very narrow domain, particularly near the initial point of contact. What I am trying to convey here is that there is a one sphere here, one sphere here, and E is Young's modulus of the sphere 1, nu one is Poisson ratio of sphere 1, and this is R1 is the radius of the sphere 1. Same parameters for the sphere 2, E2, nu 2 and R2. Now, when they are subjected to the load, what will happen? There will be a deformation of the surfaces, they will undergo the elastic deformation, and we are saying that it is not only one surface subjected to elastic deformation, both the surfaces they are subjected to elastic deformation, and this is a force. Now, question comes, is it really when they come in a contact then only they get deformed? No, even the liquid film which is generating the pressure, if applies the pressure on the surface, it can deform the surface. So, it is not necessarily only the solid to solid deformation occurs, but the liquid to solid deformation also occurs. However, Hertz was the first person who developed this kind of relation, and he mentioned deformation due to the solids. That is why we are just repeating those thing over here. Otherwise, the liquid also can deform the surface, and we need to account that deformation or that elastic deformation, which is going to finally generate elastomeric lubrication mechanism, which is the most demanded, most optimum lubrication mechanism. Now, second line of this slide says that stresses are highly dependent on the geometry of surface. We can see here very clearly, here the geometry is a sphere over a sphere, but we change sphere to the cylinder on cylinder, we will be able to find there will be different stresses. Geometry is playing a very important role when we come to the elastic deformation. Otherwise, in ordinary mechanical engineering, we assume that the geometry is not going to play that much important role as a material property are going to play important role. Or we say the elastic deformation, generally the Young's modulus, Poisson ratio will play important role compared to the shape of geometry. Well, in this case we are going to prove it, the geometry is playing important role, and if we drive the relation for the sphere or a sphere and a cylinder on a cylinder, there will be variation in expression itself. Now, these are the two examples as I say the sphere and a sphere, and just for the nice I can say this is a nice picture, maybe some sort of cartoon. Of course, for our case we are assuming there is only sphere 1 and another sphere 2. While in this case the cylinder 1 and cylinder 2, we are subjecting to the load, so that there is a deformation of the surfaces. Let us take a sorry let us take a first example. This is the sphere on a sphere, when it is subject to the load there is elastic deformation. This is again not on the scale, we are showing this deformation through the, we can demonstrate the what will be pressure variation. Otherwise, this deformation is very low. That is what we say that this B, otherwise this deformed zone which is having dimension 2B, this B in general case in real practice is much lesser than dimension of a sphere. It is not even matchable, it is not comparable, even not even a 1% of this, it will be much lesser than this. Or we say that this kind of deformation are very localized, particularly when there is a convex geometry. If there is a non-convex or a concave geometry, then deformation will be more, but pressure generation will not be that high. Well, in this case the deformation is a low, or we say the extent of the deformated zone is low, but maximum pressure will be very high, and this max pressure can go even the gigapascals. And these are the what we say that initially when we read any book, what we get the roller against the cylinder. When obviously the cylinder against the cylinder, when they are subject to a load, there will not be any with contact, there will be only line contact, but that is those are the ideal cases. In reality it does not happen. Material will subject to elastic deformation, and there will be some sort of elliptical contact instead of line contact. And when come to the sphere, again in many books we say that sphere on a sphere, this gives only the point contact, but in reality it is not a point contact, it is generally a circular contact, and we need to account those kind of contact. This is given over here. In this case, if the perpendicular to this also the dimension is B or 2B, then it will be naturally sphere or circular contact, while perpendicular direction, if contact area is so the contact patch is at 2A and A is different than B, then we can say that is elliptical contact. Now, we are able to see there is a parabolic variation, and we can take this as assumption. So, the P is equal to a pressure distribution in a contact can be given as a P max square root of 1 minus R by B square. B is a maximum value of R. R is starting from 0, that is shown over here. We say that when there is a contact patch, if I take a top view of that, and it will be a circular, and this radius will be more like a solid circle. The radius can vary from 0 to maximum value of the B, and whole pressure will be generated in this domain only. It will not be more than that, it will not be lesser than that. If only thing that the boundary case is pressure will be 0 and midpoint pressure will be maximum, that is a parabolic pressure, and that is why we are taking this assumption P is equal to P max square root of 1 minus R by B square. To find out what will be this value of the B and what will be maximum pressure, we can take a help of the load which is been applied. We say that we know the load, how much load is been applied, and we know that some geometries. So, we can integrate it from 0 to B, that is if I am assuming on one side, and there is a whole circumference. So, it will vary from 0 to 2 pi. So, this is 0 to B is radius, and 0 to 2 pi is angular extent P, and this is the elemental area or d theta into dr. If we substitute this P max P max will be common, which will remain constant, and this is represented in terms of R by B. So, we can get an integration easily. So, this is what is being given over here. We know whole expression does not depend on theta. So, integration with respect to theta is simple. It will be theta outside, and substituting value of theta as a 2 pi minus 0, it will be the 2 pi. So, this is the 2 pi has been common, P max. This is in terms of R, terms on R under the dr. So, we can take B as a common again, and P max is a common from this. This whole expression is B square minus R square into R into dr. Now, we can substitute some value for the B square and minus R square, that is what been assumed over here. B square minus R square is equal to T square. Now, we can differentiate and substitute value instead of dr, we can substitute value of T, and that has been given over here, right. So, it will be minus T square dt, and these boundary conditions will change wherever the value of the B, it will turn out to be T is equal to 0, and wherever the value 0, T will turn out to be the B, and we are assuming there is no negative dimension, there is no negative patch. Minimum value of this contact is 0, it is not negative. So, we can find out from that angle and substitute, we can derive the expression, and we say the pressure. If I know the load, applied load, I can find out in terms of B and maximum pressure. If I know what will be the hardness or at which pressure this surface is going to deform, I can find out directly B value from this expression, because P max is known to me. I can directly load is known, B max is known, B can be simply figure out from this relation. However, many times we do not know the value of the P max at which pressure this surface is going to get deformed. In this situation, we need to use additional relation, what we say the deflection relation. Maybe we can take a simple formula from strength of material books, and we can derive based on that. However, we are discussed only on a spherical contact. In this case, what we are showing is cylindrical context also. So, in cylindrical contact, there will be two axes, circumferential as well as the longitudinal axis in this case. That is why the x by b and y by a square comes over here. However, if we know the pressure variation is not going to be significant, because this geometry or this circumference is much smaller than this length. So, this pressure variation along the length is negligible. If I am assuming, or we are assuming in this situation, then what will be relation P is the same the way we have represented for the spherical contact, and we can integrate in this situation the same the way we have already done. You see the P max, this is 1 minus x by P square into dx. We can, for easy integration, we can substitute something like x is equal to b sin theta, so that we can get easy integration. Doing this, we are able to get this expression. So, f is equal to pi by 2 b into L into P max. That means, again length of the cylinder will be known to us, b is unknown and P max is unknown. If we know the definite geometry, if we know at what pressure the surface is going to deform, then we can directly find out B value. If those things are not known, then we need a additional relation, as I mentioned earlier, that we need to derive based on elastic deformation relation. That is some strength of material relation, or we can use a book, some strength of material book. So, this is what we have derived today. In this case, f is equal to, for a spherical contact this is a relation, for cylindrical contact this is a relation, and we need to determine B. That will be done in next lecture, and we will continue the same topic in next lecture. But what is interesting thing in this case is that in a spherical contact length is much smaller, or we say the B value is smaller, while in a cylindrical contact the length is much larger. So, what will happen in this situation when L is much larger for the same contact, the same area, while in this case it is happening 2 by 3 into pi, it is an 1 by half. So, 2 by 3 is 0.66, while this is a 0.5, pi remains same, value of the B assuming for timing remains same, P max when the more material have a same material strength will remain same. So, the version comes on the B versus L. That means, in cylindrical contact load carrying capacity will be significantly higher, compared to the spherical contact. We can predict from this relation, we can generally when we are trying to understand this relation. So, because L is much larger, B is not very large, and we already know that when we drive the relation, so that B need to be much lesser than radius. If it is not very small value, then we cannot use this relation at all. That is why we say that the cylindrical contact load carrying capacity will be much larger than a spherical contact. However, to get the value of B, we will start on the next lecture, elastic deformation of the materials. We try to drive the relation. Thank you.